Today we are going to talk about the Fibonacci sequence presented by Apoorva, Maddie, Lydia, Finn, Ben, and Chris. Leonardo da Pisa was a famous mathematician in the medieval era. He would frequently study the Hindu-Arabic numerical system to find new problems. However, he discovered something new, the rabbit problem.
The rabbit problem says at the start of each month, let's say you are given a pair of newborn rabbits. The month passes and there are no offspring. However, every month after the pair produces another pair of rabbits. All the rabbits will produce in the exact same way. If none of the rabbits die, because you are an amazing caretaker, how many pairs of rabbits will there be at the end of 6 months? To figure this out, we will start with our one pair in January. In February, we will still have 2 rabbits. By March, we will have 2 pairs of rabbits. By April, we will have 3 pairs of rabbits, as the ones born in February will not have produced yet. By May, there will be 5 pairs, and by June, we will have 8 pairs of rabbits, or 16 rabbits. If you look at our chart, you can see that the number of pairs is the same as the Fibonacci sequence.
As you can see, the advancement in numbers is at a very large scale. You go from 1 to 1 to 144 to 233. Each time you add the previous number, it adds up to a much larger number, almost doubling the previous one. On this slide, you can see this demonstrated on a diagram, where da Pisa mapped out just what this added spiral would look like, something similar to a nautilus shell, if anyone has ever seen those. But this is why rabbit populations multiply so much and so fast, because of this Fibonacci sequence.
The equation for the Fibonacci sequence is Fn equals Fn minus 1 plus Fn minus 2. Fn is the nth Fibonacci number and the sum of 2 previous numbers. Fn minus 1 is the previous number before Fn, and Fn minus 2 is the second previous number. Say, for example, Fn is F6, which is the 6th term in the sequence. Since Fn minus 1 is the previous number before 6, that would make it the 5th term in the sequence, and Fn minus 2 would be the 4th term in the sequence. Whatever the number of the term is in the sequence is what goes into the equation. So F6 equals F5 plus F4 turns into 8 equals 5 plus 3.
Now that you have a better understanding of the Fibonacci sequence and its applications, let's see some example problems that can be worked through with this knowledge. Number 1. Complete the Fibonacci sequence. This is the most basic type of problem that is usually seen with the Fibonacci sequence and only requires knowledge of how it works. This is a sequence problem. We're finding the 7th term in the sequence. In this case, all you would need to do is to combine the previous 2 terms in the sequence before that blank to get your answer. Combining 8 and 5 gets you 13, which is that 7th term in the sequence.
Number 2. Say you have a generational tree of mice. Starting at 1, each new generation is the sum of the 2 previous generations. How many pairs of mice are in the 11th generation? This is a modified version of the rabbit problem and just a different way to phrase the first sequence problem. When going through the Fibonacci sequence, you only need to find the 11th term in the sequence, and in this case, there would be 89 pairs of mice in that generation. Number 3. A farm starts with a single pair of rabbits. The rabbits mature and start reproducing after 1 month. Once they start reproducing, each rabbit pair produces 1 new pair of rabbits every month. Assuming that no rabbits die, how many pairs of rabbits will there be after 8 months? Since there are limited ways to phrase a Fibonacci-related word problem, we've come back to using rabbits and their generational tendencies. Since every pair of rabbits produces 1 or more rabbits, their generational tree expands exponentially following the Fibonacci sequence. In this case, we are finding the 8-month count of rabbits, or the 8th term of the Fibonacci sequence. 8 steps into the sequence, we would have 21 pairs of rabbits.